Hello, and welcome to the fourth training module of the State Configurable Timer. This is the agenda. First, we'll go through an introduction of the graphical configuration tool which we're going to use to program the SCT. Then, we will look at what it means to generate a basic PWM output. PWM stands for Pulse Width Modulation. Then we'll go through a high-level view of our target system. In this case, it will be the control logic for a brushless DC motor. Then, we're going to design the state machine diagram using the graphical configuration tool. At the end, we will integrate the output of the tool within an example project and build our test application. Before proceeding into this training module, make sure to have the SCT tools installed on your computer. To help you on this, you can refer to the Designer Install Guide or to the first training module of this series. To start the training, please make sure to have this template file, template-split.fzm, available. This template is shipped within the examples available for the finite state machine design tool. Let's switch to this tool and have a look. To use the template split.fzm file, just open it by double-clicking on the file. At this point, the graphical configuration tool should open up and show you the following screen. This is what you should see after opening the template file. As you notice, there are some items in the configuration which have been predefined, since they are used for every SCT configuration, or are common to most of them. One of those is the entry state. This represents the initial state of the SCT as it starts, so every application will have an entry state. Note that L entry and H entry are relative to each half of the SCT counter. This template will be very useful for users which need to use two 16-bit timers. Note that there is also another template available for an SCT configuration based on the 32-bit timer, which is called template-unified.fzm. Within the tool, L entry and H entry are reserved names, so please do not rename them or the tool will not be able to generate a valid configuration. All other state names in the state machine can be defined by the user, and in fact we will create some new and assign them names later on. There is also another state being defined for each timer half. This is the L always and H always state. This is also a reserved name, but defining and using this state is optional, so you can delete it if it is not used in your state machine diagram. In fact, this is a pseudo-state, which means it does not relate to a specific state of the state machine. It is just a shortcut to indicate that whatever transitions or actions are being linked to this state, these will have effect in any state of the state machine. It is just a graphical shortcut, so that you can avoid drawing the exact same event in all states of your state machine diagram, which could save you some time. On the upper left, you can see also a global configuration table, which is used to define global settings for the diagram. In this table, you can find things like the timer mode configuration, unified or split, the list of input signals, the list of output signals, and the list of events used to define the state machine diagram. There is also a reference to a file which has to be included. This text file can be modified in a text editor and is used to define the assignment between the logical inputs and output names which you can specify in the state machine diagram and the actual physical inputs and output pins of the SCT that you want to assign them to. In this example, you can see that we have assigned the input pin, which we named pin input, to the physical pin of the SCT number 0. Similarly, we have decided to assign the output pin, which we called pin output, to the output SCT pin number 0. The other output available, which we called pin output preset, has been assigned to the SCT physical output number 4. The upper part defines some general capabilities of the SCT block. In this case, we don't have to edit this, since we are going to generate a configuration which can run on the LPC1800 or LPC4350 series of microcontrollers, which have the hardware resources which are listed here. Now let's have a look at what the global attributes are like. Let's start from the state machine part. In this global properties, we can see a couple of things we mentioned before. The first thing you have to specify is which include file you want to use for the state machine. In our case, it's template-split.inc. As mentioned, this is used to specify the association between the input and output signals and the physical pins of the SCT. IsUnified is related to the timer configuration. In our example, we are going to use one 16-bit timer half, so we can leave this as 0. Now let's move to the other tab, Inputs. Here we can see the inputs that we want to define for our state machine. The first one we have defined is called pin input. In this case, this is a physical input pin. The other two, which we called L counter match and H counter match, are also in a generic sense inputs to the state machine, but are not physical inputs. These are related to the timer. In this case we can see it, since the input source for this input signal of the state machine is defined as a match condition. The match condition can be found on the right hand side. In this case, L counter match is defined to be when the L counter is equal to a numeric value which we specify or name as match L count value. Similarly for the H counter. In the other tab, Transition Events and Outputs, we see a much more detailed list. The interesting part of this table is the left-hand side, where we can define a name for the output. On the right-hand side, in the type column, we specify that this signal is of type output. On the preset value column, for a signal which is of type output, we can specify whether the signal at the beginning of the application has to be to a specific level. In this case, we can see that the pin output preset has to take the logic level value high when the system starts. In this sense, we put here a 1. Default value would be 0, and this is the case for pin output, which is not shown. There is also another example of a transition type, which is called captured value. Here we show how the setting would look like when the transition type would be for a capture event. We will have to specify the type capture in this table. The preset value in this case is used to identify to which of the two timers this capture event has to be mapped. In other words, to which timer half it refers. The preset value has to be set to H for a capture event which is related to the high side of the timer, to L for a capture event which is related to the low side of the timer, or has to be set to U for a capture event which relates to the unified timer mode. If we scroll down to the list, we can see another set of transition events. These are events which relate to the internal logic of the timer. The predefined events allow us to stop the timer, to limit the timer, to halt the timer, to generate an interrupt to the processor, or to generate a DMA request. We don't have to specify any value within this table for those events. We are just going to declare them so that when needed we can use them in our state machine diagram. Note that since the tool has been adopted from an existing one, not all the settings, which are very generic and can apply to any state machine, are of use in our case. So to quickly recall, we just go through again all the relevant inputs and outputs and table entries that you have to use to define any event which will be used for the SCT configuration. These are the relevant parts related to the state machine configuration. These are the relevant parts related to the inputs configuration. These are the relevant parts for the outputs configuration. Now let's go back to our state machine diagram. As you can see, we have defined two example transitions. The left one is simply based on a counter match value, which we called H counter match. This transition has been defined in the global table we just saw, and we can see it recalled over here. This means that when the timer will match the value match H count value, which is a numeric value, this transition will happen. The actions this transition will take will be to clear the physical output, which we called pin output preset, to 0, to generate an interrupt to the processor, which we called my IRQ, and to generate a DMA request on DMA channel 0. On the right hand side we can see another example transition. This has been defined to happen when the input signal pin input has a rising edge, which is identified by the symbol plus. When this event is active, the output pin, which we called pin output, will be set to value 1, and this event will also generate an IRQ, which we called again my IRQ, and will generate a DMA transfer request, this time on DMA channel 1. For more information about all the options that are available for specifying transitions between states, you can refer to the tool's user manual, which has a complete list for all of them. Just to quickly recall, a PWM waveform is basically a square wave which has a defined period of repetition, and within each period is characterized by a duty cycle value. The duty cycle value is a percentage, which indicates the ratio between the amount of time the signal is turned on versus the amount of time the signal is turned off. This picture shows an example of a PWM waveform within one period, where you can recognize the elements which I spoke about. In this example, we can see a PWM waveform which has a duty cycle of 20%. This means the PWM signal is turned on during 20% of the total period time. We will use this basic example as the starting point for creating our configuration. In this diagram, the red lines represent the SCT counter value. As you can see, the SCT in this case is configured to count up, so the counter value starts from 0 and increments by 1 at each clock tick. In order to create a pulse, we have to define two match values. The first one, in green, defines the point in time at which the output, in blue, needs to be driven low. The second one, in orange, defines the end of the period and is configured to limit the timer. In fact, as you can see, the counter value is set back at 0 and the SCT restarts counting. At the same time, this event also sets the output signal back to logic level high. This, of course, is just a simple example. Since every event is fully configurable, you can define whatever action the hardware needs to perform on the outputs, like setting, clearing, toggling the output, or also no change. We will assume that our system looks like the one in the following diagrams. This first one shows the motor part. There are 6 PWM output signals, each of which is used to drive the power transistors shown in the power bridge, which are acting as switches. Those 6 PWM signals are going to be generated by 6 dedicated output signals of the SCT. On the right hand side of the picture, you can see a representation of the motor windings, and the curved arrows with the numbers represent the sequence in which the current will flow through the windings, depending on the switch's configuration. This table details the switching sequence. The sensors being used for determining the motor position allow to track the motor rotation with a precision of 60 degrees, where a full rotation corresponds to 360 degrees. As you can see in each interval, different signals need to be driven in order to properly excite the motor windings. The last column indicates which switches needs to be active in each sector. During a clockwise rotation of the motor, the SCT will cycle from sequence number 0 to number 5, restarting then from 0 once one rotation is complete. The sequence numbers on the left of the table correspond to the current flow sequence numbers we have shown in the previous diagram. The feedback signals for determining the motor position are provided via 3 Hall sensors. Each sensor H1, H2, H3 provides a square wave type of signal, which you can see at the top of the drawing. The voltages EA, EB, EC over each winding of the motor and the relative current flowing in the coils are shown in the bottom 3 lines of the diagram. By evaluating the edges of the signals, we can determine in which sector of a full 360-degree rotation the motor is actually into. This information is used to decide which of the 6 phases need to be driven at any time, since the activation of the switches depends on the position of the motor within each 60-degree sector. The 3 signals generated by the sensors are going to be used as inputs for our SCT configuration. Now that we have a better idea of how our system should look like, we start by modifying the template. At this point I have just renamed the 2 template files to something more meaningful, like mcbrushlessdc.fzm and mcbrushlessdc.inc. To reflect those changes, we are going to modify the global attributes of the table. So let's start with the include file. As mentioned, the timer will be configured in 16-bit mode, so the value is unified will be left at 0. Now we proceed to define the inputs which we are going to use. These will come from the 3 Hall sensors we mentioned. So we are going to generate those and call them, for example, H1 for the first Hall sensor, H2 for the second Hall sensor, and H3 for the third Hall sensor. Since these are physical inputs, in this table we don't have to specify anything else. Let's delete these 2 predefined inputs and create our new ones. To generate our PWM waveform, we would need a couple of match values. The first one is going to define the middle of our PWM period. So we will call this input period middle. This event is going to be associated with the low half of the timer. So we define this to happen when the low side of the timer will be equal to what we call PWM middle. This numeric value will represent the middle of our PWM period. Then we will need an additional match event to define the end of our period. So similarly, we just insert a new match defined event, which we will call period end. This will be defined to be when the L counter value reaches the numeric value PWM end. To generate a single PWM pulse, we will need also a match value to determine when the output needs to be switched. So we will have to add another input type. We call this value match 1. And we define this value, or this event, to happen when the L counter value will reach match 1 value. This is also a numeric constant which will be defined within our application. So let's move now to the transition events and output section. First we start deleting the predefined outputs since we want to rename them to a more meaningful name. We are not going to use any capture register, so we can delete also this predefined event of type capture. Since we are going to use only the 16-bit lower half of the timer, we can also delete all the transition events which are related to the high side of the timer, since we are not going to use them. In this simple example, we are not going to use any DMA type of transfer, so we can also delete DMA0 and DMA1 type of transitions. In this example, our counter will always run free and will never be halted during the application's lifetime, so we can also delete the halt event. Similarly, since it's going to run free, we're never going to use any hardware event to stop it, so we delete also this one. Now we can start adding our own outputs. Consistently with the diagrams that we showed during the presentation, we are going now to add the switch signals. These signals will be used to drive the switches for the power bridge to the motor. Let's start to define one of those signals, which we will call switch 1. In this case, the type will need to be specified output. Although it would be the default value, we specify this signal to be at a preset value logic 0. For the first sector, we will need also another output, which will be the one driving switch number 6. Similarly, we specify this event to be of output type, and we set its preset value also to 0. Now we have entered enough information in the global table to be able to draw the first simple part of our diagram. So let's go back to the drawing. As you noticed, all the entries that we have deleted have disappeared from the diagram. Similarly, since we are going to use only the low side of the timer, we are going to delete also the states which are related to the high part of the timer. Now we are going to delete this transition, since this is not defined anymore. This leaves us with a very simple diagram without transitions, and based on this we are going to build our new diagram. In each state of our state machine diagram, we are going to use the same event to define when the middle of the PWM period has been reached. So that's why, from within the always state, we add a loopback transition. Within the properties of the event, we can define a name for this transition. Let's call it transition middle of PWM period. This is just a name which will not be used in the diagram. This could be useful if we want to find out how the tools has internally mapped the logical resource we are defining here to one of the physical resources available within the SCT. In the equation field, we have to apply a value for this attribute. If you remember, we defined before a transition, which we called period middle, to be associated to a match event. This match event happens when the low side of the timer gets to the value PWM middle. Now we are going to use this predefined match condition to define our event. So we put the name period middle within the equation field. Since we want this event to act as a limit for the counter, we put the value 1 within the field LLimit. We don't want this event to generate an IRQ or have any actions on the outputs, so we leave everything else empty. This shows now how our defined event will look like. As you see, it is a loopback transition, which means it doesn't change the state of the state machine, and when the condition period middle, which we defined to be in this way, will happen, the counter will be limited, so the limit condition for the timer logic will be set. In our application, we assume the entry state will be related to the first sector of the motor's rotation. Now we will define the event which will be responsible for setting switch number 1 and switch number 6 within the first sector of the motor's rotation. In this case, we will add a loopback transition to our entry state. We call this transition sector 1. This event should happen when our match value number 1 is reached. The effect of this event will be to set switch number 1 and switch number 6. Now we accept the inputs. Now we have defined a loopback event which will happen within state L entry, the entry state of the state machine, and which will set the outputs called switch 1 and switch 6 when the value match 1 has been reached. This will be configured by our application depending on the desired duty cycle within the first sector. State L entry is related in our application to sector 0. So now we will add a new state which we will relate to sector number 1. In the state properties we can define a name which we will call sector 1. If you remember the principle related to the Hall sensor feedback, we can determine when the motor has rotated into the next sector by observing the Hall sensor outputs. In particular, we will be able to determine when the motor has rotated or moved to the first sector when the Hall sensor signal H2 will be high. To make a controlled transition between one sector and the next, we are going to evaluate the level of the Hall sensor only at the end of a period. So now we are going to add a state transition to sector 1 from our entry state, which is sector 0. Now let's edit the properties of this transaction. Let's call this transaction sector 0 sector 1. As we said, we want this transaction to happen only at the end of a period and when the Hall sensor level coming from sensor number 2 is high. This is how we are going to specify this event. This event will be used just to move to this other state machine state. So we are not going to make any change to the output signals or to trigger any new condition for the internal logic. Now we can see that we have defined this new transaction. So at the end of a PWM period, in case the Hall sensor signal number 2 will be high, we will jump to sector 1. The difference now is that within sector 1, a different pair of switches need to be activated. In this case, it will be switch number 3 and switch number 6. So now we need to define a new event, which we are going to add to the global table. First, we add the missing output signal, which in this case is switch number 3. This is also an output type. And we want its preset value for safety to be set at 0, so that the bridge is not driven. Switch number 3 has been added to the list of outputs. Now we will add a match condition, which will be used when our state machine is in sector 1. We will call this match condition match 2 and define this to happen when the low counter reaches match 2 value. This allows us, if desired, to specify a different duty cycle value for the second sector of the motor rotation. Now we see that our match condition has been added to our global table. Like we did for state L entry, we are going to add now a loopback transition, which will be used within the second sector of the motor rotation. We will call this transition match 2. And we want this event to happen when the condition defined by match 2 is valid. In this case, we will need to drive switch number 3 and switch number 6. When the state machine jumps in sector 1, the event named match2 will be active when the low side of the counter will reach the value match2 value. One thing to notice is that the event named match1 will not be active anymore, since now our state machine is in sector 1 state. Instead, the event called period middle will be active also in sector 1, since we have defined it within the always state. Now, we can extend our diagram for all of the following sectors. Now we have defined a new match event, which will be active when our motor is in sector number 2, and in this case, switches number 3 and number 2 will need to be activated. We can continue our drawing for all of the sectors up to sector number 5, after which the motor will have completed a full rotation and will return to the state L entry. Let's move on and see how our complete diagram will look like. As you can see, there are a total of 6 different states which are associated with each sector the motor will rotate into. The transition events between those states are defined to happen at the end of each PWM period, but will happen only when the whole sensor feedback signal will have the appropriate level. For each of those states, the event named period middle will limit the timer. This event is associated with the middle of the PWM period. The counter will be configured in up-down mode. This configuration is outside of the state machine configuration and will be defined within our application code. In this mode, the events like match1, which set switch number 1 and switch number 6 when the counter is in the up count phase, will clear outputs named switch number 1 and switch number 6 when the counter is in the down count phase. This allows us to get a symmetrical PWM waveform in respect to the middle of the period, and also assures that at the beginning and at the end of the period each of the switches will be opened, which is a safe condition. If, for example, we would like to get a CPU interrupt at each motor rotation, we could add this to the event defined for the last transition of our diagram. We could do it, for example, in this way. Just double-click the event, and within the IRQ field, give a meaningful name for this type of event. We call it My IRQ. In this way, an interrupt to the CPU will be generated every time our state machine jumps from sector 5 to the entry state, which means every time a full motor rotation will be completed. The tool will generate a macro which will be related to the My IRQ name we gave before. This macro will be used to map the physical event which the tool will internally select to configure the SCT to this interrupt condition, so that the C code will be able to use this macro to check if the interrupt flag is active or not. Now we are done with drawing our state machine diagram. In the next step, we are going to open up the example project which is delivered with the SCT configuration tools and which is based on the Kyle development environment. So now we double-click on the brushless DC motor example project and the following screen should open up. Let's have a look at the relevant files we still need to edit. In this case, it will be the mcbrushlessdc.inc file, the include file that maps the logical names for our input and output signals to the physical output and inputs of the SCT. For example, we specified the input Hall sensor signal H1 to be linked to the SCT input number 4, and we assigned the output for the switch number 3 to be the SCT output pin number 2. We still need one thing, which is to define the numerical constants that within our diagram will be used as match values. This is done within the sctuser.h file. The values that we have to specify here are the match values that we used in our diagram within each of the sectors. In this case, they are all set to the same value, but you can set them to any value you want. Similarly, we define the PWM middle value to be set to 300 and the period end to 0. All those values are specified in timer ticks, which means the period duration and the switching points will be determined by the frequency at which the SCT will run. So now we can build our project to debug our application. SCT_FSM.c and the related header file are the files which have been generated by the tool. In the first comment you can see a summary of the physical resources of the SCT that were used by the tool. Then follows a list of all the register settings for the SCT. In the header file for the SCT configuration, we can find some macro definitions which can be useful in an application code. For example, the macro SCT IRQ event _ my IRQ defines the mapping between the logical interrupt event we have defined in the diagram and the actual physical flag which will be associated to that interrupt event within the interrupt register of the SCT. Then we have a summary of the input and output assignments we made. We can see this is strictly following the assignments which we have specified in the user configuration file sct_user.h. We also have a summary of the preload values for all the switches. We specified them to be all set to 0. Further down, we can find some additional macros which can be used for match register reloading. In fact, during the application's lifetime, it will be necessary to change the duty cycle of each PWM waveform. To make the programming easier, since the tool took care of mapping the hardware resources from our logical diagram, those macros have been defined. For example, by calling the macro reload match1 with a value, the application will be able to load the new match value into the associated match register which have been linked to the specified event. In this way, the user does not need to know which actual hardware resource was chosen by the tool to configure the SCT, and makes this transparent. Now we are done with the last of our SCT training session modules. Following this tutorial, you should now be able to use the finite state machine design tool to create your own setups and applications. Thank you for attending this training session and have fun in programming the state configurable timer.